Morning, everybody. We'll get started with the webinar in a few minutes here. Just give everybody a few more minutes to get into the meeting. So in about 2 minutes, we'll start off. Thanks. All right. Good morning, everybody. Welcome to the next Odell Connect session on fan curves and system effects, where we're going to explore how system design and fan performance interact in real-world applications. Before I introduce our speaker for today, I want to note we're going to have a few documents located in the chat section to help you follow along with everything that Ron talks about. And as a note, questions, please feel free to put them in the chat. And as they come up, I'll step in and let Ron know we have a question, or feel free to save them till the end. We'll have about 10 or 15 minutes there. So for today, we're pleased to welcome Ron Michael. He's a regional manager at Loren Cook. He is specialized in fan engineering and field application management for over 2 decades. He has a deep understanding and expertise in building ventilation, lab systems, fan sound and vibration, and active involvement in ASHRAE and AMCA. Ron brings a practical engineering-driven perspective to today's session. Thanks so much for being here, Ron, and I'll hand it over to you now.
All right, great. So thanks everybody for taking the time to let's see. I need to share my screen. Okay, can everybody see it? Let's see. So we up and going?
Yep, you're good now.
Excellent. So listen to everybody. Thank you all for coming, especially if we've got any younger engineers, that maybe have graduated from in the last 5 years. Maybe you've just started. We're gonna condense 2 topics that typically can take an hour each. We're going to condense it down into some finer tuned understanding of fan curves and system effect. If you all want a little bit more detail, we'll be more than happy to come and present in your office. We're also planning some local engineering seminars where you can come and you may hear some of the same things, but in a little bit more detail. Obviously, when we get started here, when we talk about fan curves, it's probably not the most exciting topic that you've ever heard. I will agree with that. It's kind of a funny story that I like to tell before we get started, especially again for the younger engineers. The reason why we cover this topic, many years ago, is over in Boston, in North America, obviously in the States, and I had come out of our engineering department and was doing some of my first engineering visits, and I just assumed everybody knew how to read a fan curve. I thought, well, that was a given, until I found out that the head of the mechanical department from the largest engineering firm at that time in Boston really couldn't tell you how to read a curve. So I'm going to go through this relatively quickly, okay? Um, if you want a little bit more, the presentation is available to you, and we'll also be more than happy to come and present in your office, especially to the younger engineers. All right. If you understand how to read a fan curve, I can tell you you're automatically going to be in the 90th percentile of mechanical engineers. I really want to stress that. So, uh, for any of, again, the younger engineers, if you want to print these sheets out, you can print them out, follow along in your attachments. Uh, Again, I'll be going rather quick just so we are able to cover a lot of information in a short time. So in your handouts, we're going to look at an unstable curve and a stable curve and get an understanding of the two, right? We're going to look at a multi-speed curve. Uh, Obviously, you all specify a lot of VFDs, and you're starting to use a lot of EC motors where you can make adjustments, things like that. And then I'm going to show you just briefly, if you follow with how to read a fan curve and you follow the technique I'm going to show you, uh, you'll be able to understand the characteristics of all the different fans we have. There's a reason why we have all different types of fans, depending on how much air you need to move against how much resistance, which would be what we will refer to as pressure drop. Okay. And again, the reason why we're going to start with fan curves is no matter how good your actual calculation is on your job, no matter how good the calculation is, if you select the wrong fan based on characteristics and you select the fan on the wrong part of the curve, it doesn't matter how good your calculation was, you could still run into trouble. All right. So I'm going to show you a technique that you're really not going to see anywhere else, uh, just based on some of the things that I've learned over the past 2 decades. I think it will really help you out. Okay, so I'm going to talk a little bit about these characteristics at the end. These are all in your handouts. So where do we start? Well, we start with data, right? We start with data, and I want to just specify, just clearly point out a few things whenever you see any printed data or you see the data that comes out on your selection programs. And this is applicable to all fan manufacturers. The data that you actually see is our test results. If from time to time over the years, if maybe there's been a little field issue and an engineer wanted to see our actual fan test, that's what our catalogs represent. It's the actual fan test, both in printed form and also in the computer program form, the electronic form. It's the exact same data. One is printed, one's electronic. But one of the strong points that I want to make for you, and it's a question many of you have probably heard if you've heard me speak before. I always ask the question, is or all are all published points good selections? If you go in and use any manufacturer software, uh, the first big mistake that most engineers make is they assume all the published points or all the points on the computer programs are good selections. And I'm going to prove to you that the answer is no. not all good points, not all points that you see in a catalog or see on a computer program are good selection points. I can't stress this enough. You probably will not hear this from other manufacturers. If you get somebody that's relatively new from a fan manufacturing company, they're probably going to assume like you that if there's data in the catalog, that it must be good. And this is the main thing I want to show you when it comes to understanding fan data is that not all points are good selection points. Okay. What that data represents is the AMPCA 210 and 211 test result. Now, I'm not going to get into the AMPCA details. We would be here for hours. But whenever we say AMPCA, AMPCA is basically the way I try to describe it as our league. You know, we have you have, guides that for like motor companies, fan companies, pump companies, coil companies, like an ARI test result or a NEMA test result. So, who are members of AMPCA? All the companies that you've heard of regarding fan or airflow when it comes to mechanical equipment. You know, Loren Cook, Greenhack, Twin City, Penberry, we're all members of AMPCA. All this guarantees is that you're looking at a product that's been tested the exact same way. Greenheck doesn't test different than Cook. We all follow the exact same guides. Okay. And that's what our test data represents. The big misunderstanding, whenever I was talking about whether you have, if all points are good selections or bad selections, is we are giving you the full range of operation. And I like to say it as from stable points to unstable points. And I'm going to show you here in a few minutes on the fan curve what we mean by a stable selection as opposed to an unstable selection. Okay, so we're giving you the full range of our test from stable to unstable, which hopefully would tip you off that, again, not all points are good selection points. Okay, we base them all on standards, number of standards. Obviously, the first important one is zero elevation, 70-degree airflow. You know, all the data is based on the exact same conditions for all the manufacturers. Okay, and fortunately, they're based on perfect lab conditions. Now, sometimes this is where you can run into a big challenge in the field. Okay. And I'm going to talk about, I'm going to actually expand this a little bit later on when we get into system effect. I'm going to show you that the same exact rules for fan inlets and outlets are actually the same rules for all the products that you use on jobs. Okay, so if we looked at some data, again, I'm going to run through this real quick. I just want to kind of point out a few critical things on the fan curve. All right, whenever you see this data is exactly the same as the data you see in the graphical form, which is your fan curve. Okay, so you'll see a single fan curve called the CFM and static pressure curve. And then you have what's called a design point of operation. Now, I'm going to kind of slow down here a little bit and tell you, what makes up a design point of operation? Well, it's CFM and pressure. In a few slides, I want to make sure that you make a note, especially again, I've referenced the young engineers. One of the big things that you have to understand is whenever you're doing your calculations for CFM and pressure drop, you have to understand that those are estimates. Very rarely are you going to fall exactly on the air number and the pressure number in the field. Okay. Remember, we're testing in ideal conditions. You're working in anything but ideal conditions, right? So you're trying to do an estimate, or you're trying to figure out the flow and the pressure. And at best, you're working on an estimate and you're trying to hit as close to the estimate as possible. Remember that, and I will remind you of this in a few slides. Okay. But this is basically the way you would understand the data below and how it relates to a CFM static pressure curve. Then you have a CFM horsepower curve. Okay. Same thing, right? When you combine the two, uh, you're simply overlaying multiple curves on one piece of paper. There's no reference to where these lines cross. It's two separate pieces of data on the same curve. Okay. And then you have a surge line, and I'm going to explain to you where we determine where that surge line is. Okay. So if we're doing a test, again, I'm going to run through this quickly. If you want, again, an in-house visit, we'll be more than happy to come in and do an in-house visit and review this information with you. What's the first point that we would actually test? It would be what we call free area. How much air are we moving against zero resistance? So when we're doing the test, we actually make adjustments and we add a little bit of pressure drop, in this case 0.125, and we plot a point. You'll see I got rid of the fan curve because all we're doing is plotting points, and then we're going to connect all the dots, and that's what's going to give us our shape, or the characteristic shape of that particular fan. All right. Now, if you really want to follow along here, notice my horsepower and my airflow once we get down here to the end, right? So if I make another adjustment, I add a little bit more pressure drop. I've got that point at a quarter inch, okay, 0.375, 0.5, 0.625 inches of pressure drop. And I want you to remember this point because we're going to come back and talk about this point a little bit later. This is your sweet spot. Okay. This is the point. This is that range where you really want to concentrate on a good selection, right? Many years ago, and I'll show you this here in a few minutes as well, before we had computer programs, engineers would say you want to be about 3/4 of the way up the fan curve. Well, what that meant was you want to be about 3/4 of the way down the tabulated data. This is where your best selection point is. So if you look at our horsepower, we're at 1.65, 3/4, we're at 1.66. And then the very last point we publish, you'll notice that the horsepower just dropped off to 1.44. The airflow fell off a lot. We've simply maxed that fan out. We've maxed out the ability for that fan to do any more work. Okay. And we connect the dots, and that's what gives us our shape. But you'll notice that's also how we determined our do not select line, as you can see right here, okay, in the purple color. Okay. So we simply tell you, you don't want to work and select anything over in that area. Okay. So you got an unstable point. I'm going to kind of pick it up here a little bit. What really defines an unstable point? Well, I told you that your point of operation right there is an estimate. So what I try to educate young engineers on is, if that's an estimate, okay, and we want to know why this is unstable, highlight a range. Take a highlighter, highlight a range. Since it's an estimate, you may be operating anywhere in this range. Well, a lot of people will say that's a very broad range. Not necessarily. What I'm going to instruct you to do next is dash lines over to pressure drop, and you're going to see we're just over 1/10 of an inch from 0.8 to just over 0.9, and then dash lines down and look at the wide range of flow. Basically, a small pressure change is going to reflect in a large CFM change, and that's why we call this an unstable selection. The most important thing to remember, though, is this is a published point that you can still look at in the catalog, and in some cases get that same selection on a computer program. Obviously, you don't want to do that. Okay. So now let's look at a stable point of operation. If we look at a stable point, again, what's the best area, your sweet spot, 3/4 of the way down the tabulated data, or 3/4 of the way up the curve. So kind of coming down to the end here, what's the first thing we're going to do? We know that is an estimate. And I also like to add in at this point, maybe on this particular fan, you may have this fan running on a VFD, or you've got a control device, something that's going to tell either the VFD or the EC motor to adjust speed. So I'm going to highlight a range. The range is arbitrary. I'll give you a little bit of a guideline here in a few minutes. But again, if I dash lines over, now I've got 4/10 of an inch of difference, and my airflow difference is much less, which means we're what we would call in a very stable region. Okay, just as a little review. Like I said, if anybody wants a more in-depth review of how to read curves, we'll be more than happy to come and do a lunch and learn or something like that in your office. All right. Well, when I talk about this range, how much range should you give yourself? If you have a very simple system, you don't really need much of a range. All right. A simple system, you can highlight a small range. If you're doing a much more complicated system, like a lab system or something that's got a lot of different controls, you obviously want to highlight a broad range of where you may operate. Okay. And then if we take the same selection, okay, and we adapt it to a multi-speed curve, it's the exact same fan. Now we can simply see where we're operating. And if you look at your high side and your low side, you'll know that you can operate anywhere in this range as you have adjustment in your system. Okay. Right. And then just coming down to the very end of this, if you wanted to know what the characteristic is of the different type fans that we have available, you can use the exact same guide. Highlight a range, dash the lines over to pressure drop and flow, and you're going to understand the characteristic of that individual fan and what its capabilities are. Okay, so there's a mixed flow characteristic and there's an axial characteristic. Again, the best way to understand what the characteristic is of that individual product is make your selection for CFM and air, CFM and pressure, highlight a range, dash your lines over and down, and it's going to tell you what's going to happen if I'm a little bit off in my pressure estimate, and it's going to show you how much airflow you're either going to gain or lose based on your estimate. Okay, so that's a quick introduction to fan curves. Okay, now I'm going to switch over and I'm going to open up our system effect presentation. And on this one as well, I have reduced it just a little bit, but I want to really show you all, especially the younger engineers, I'm going to point out a few items, okay? So really, this is the base of why this presentation exists, okay? Uh, why does an AMCA rated fan sometimes fail to perform in a system? Well, hopefully most of you will look at that picture and you'll have a pretty good understanding of why the performance is most likely way off. Okay. I appreciate, I saw a smiley face there. Okay. Uh, but I'm gonna really try to simplify this for, again, many of the young engineers uh, by giving you and showing you a few handouts that you should be able to reference, keep handy to as reference guides, so you avoid this mishap right here. Okay, all right, or a mishap like this. All right, these were obviously systems produced by people that didn't understand things like rotation, discharge, straight inlets, straight outlets, and there's a reason why somebody took a picture of it, because the system just was not working. Okay, so in your handouts, we've given you uh, a little guide, a guide on correct and incorrect installations. Okay, you'll see these a little bit, again, a little bit later in the presentation. Okay. I also added a second handout, and I want to make sure everybody knows this handout technically is really not, let's say, an official handout. I'm going to call it, getting you within a 90% understanding of all the other products that you work with. Uh, you see the guideline for fans, but you can apply the same guideline for any products that you deal with. Fans, duct components, coils, heaters, humidifiers, airflow stations, I could go on and on with all the different products. Well, think about it. Where were all those products tested? They were tested in an ideal lab condition. What are the ideal lab conditions? Laminar flow in, laminar flow out. So what the gray box represents is any typical product that you work with in a system, right? A duct heater, a humidifier, a coil, uh, any of those items still need laminar in, laminar out flow. Okay. I also introduce rotations and discharges. Okay. Very important to understand, especially again for the younger engineers. And let me give you uh, a little understanding for any of you all that are working a big office, a large engineering firm where you've got some engineers that, like me, are a little bit older and seasoned. Okay, I want to make sure everybody understands why I'm really going to hammer the understanding of rotation and discharge. For many of the firms that are still using AutoCAD, I know a lot of firms still use AutoCAD as well as Revit. Well, in AutoCAD, you could draw a box with an X through it and call it a utility set fan and leave the determination of rotation and discharge up to the the mechanical contractor or the sheet metal contractor, right? Um, that basic guideline is changing a little bit. And why it's changing is many of you all are now starting to use Revit. And now that you're using Revit, there's a little bit more skin in the game, if I want to put it that way, because now you're actually bringing the model in. You just can't leave the rotation and discharge up to the contractor, because you've got to pull that basic model in, which means ultimately you're kind of deciding that. All right. So I want to just point out a few critical things here. All right. Um, your rotation and discharge Oh, sorry about that. This sheet is adapted from an AMPCA standard, standard 99, which means it's the same guideline for all the other fan manufacturers. Second thing to identify here is the understanding that rotation is viewed from the drive side. I'm going to show you some pictures here after a while of absolute disastrous jobs that ended up costing, either the contractor or the engineering firm a lot of money because they didn't understand why we have the different rotations and discharges. They probably never saw this sheet that's part of your handout, and they had no idea that the rotation was viewed from the drive side. So you're going to understand. I'm going to try to give an understanding of how important this sheet is. And for any young engineer, it's one that I would literally hang up in my workspace, especially for the young engineers working in Revit. Okay. So again, we come back to the beginning. It's all about performance tables. Uh, I remind everybody, if no matter how good your calculations are, if you pick the wrong fan or pick it on the wrong fan curve, you're really going to run into a lot of trouble. So I'm going to show you real quick 4 slides. It will be fuzzy at first. I'm going to go quickly, but I'm going to show you basically where we're going to end this presentation. Okay. Uh, just to give you a basic idea of why I'm going to talk about uh, understanding locations of where the air balancer read his readings, understanding the effects of accessories, understanding where we're selecting on the curve, and then we're also going to talk about system effect factors when you don't have a good inlet condition. Okay. So, if we look at a typical job that you're working with, okay, and we see, you've got a CFM and static that you've selected, right? You've selected it on a good part of the curve. You've done a pretty good estimate. You kind of covered yourself on being on the high side or the low side of your estimate. And then what happens is, okay, hold on a minute. I don't know why this is getting caught up. Oh, then what happens is the air balance report comes back, okay, at a lower airflow and even a lower pressure drop. Well, one of the things that you're going to hear me say a few times, the biggest mistake that, let's say, air balance companies make is they give you one sheet of paper. You're going to hear me say this again here in a few minutes. And they never tell us where they're measuring the fans. So we're going to talk about the effect of accessories, locations of measurements. And in this case, what we're going to do is I want to make you all understand that uh, we can help you with an air balance report. In this case, now I've got to manually add in, let's say, the pressure drop of the damper, and I've got to manually add in a system effect factor, and then we're right back on the curve in order to determine what we have to do to meet the actual performance. So air balance reports are obviously always required. The biggest misunderstanding with air balance reports is they don't tell us exactly what the inlet conditions and outlet conditions were like and where they measured from. As long as they do that, we can usually go in and solve the problem. So this is what you run into again from time to time. So here we are back at our picture, and I want to just run through some stuff rather quickly on basics of the way we test, right? And then we'll get into some other kind of boring details, but once I get to the actual job pictures of disasters, I think it will be somewhat entertaining. All right. So I've got, again, that same picture. Why does an AMPA rated fan sometimes fail to work in a system? Well, in order to avoid that, we're just going to get a basic understanding of how fans are tested, how the calculated performance, and then the reason for the loss of performance. If you want to know how fans are tested, just look at the little handouts that I sent accompanying you on correct inlets and correct outlets. That's basically what we're telling you that you have to do. Because when we do a fan test, again, we're following an AMPA standard. I don't want to get that deep into this. If you see an AMPA standard, it guarantees that we're all doing it the same way. Every manufacturer, whether it's Cook, Greenac, Twin City, Pinberry, any of the companies, we're using uniform setup methods, and we're testing everything the same way. Okay. Then what we do is we'll send all that data to AMCA, and they'll certify the data. So they'll actually take test data from, let's say, the Cook lab. They'll select random fans. We'll send them to Chicago to the AMCA lab, and they'll test them on both labs, and the data has to fall within a very tight percentage to actually receive a certification. Okay, so really all the manufacturers' data is certified on the same lab in Chicago. Okay, so here's a test chamber. Okay, it's basically a big box that is intended to replicate as close as we can what your system would be. Obviously, we have to use some kind of a controlled device that everybody can use. So basically, everybody's test chambers are the same. It's simply a way of measuring what external pressure effect will have on the actual fan itself being tested. Okay, so this is a basic way. Again, I don't want to get too deep into the fan test because it could take hours. Okay. Obviously, we have nozzles that adjust that record velocity. Um, I try to explain it this way. If we're testing a very large blower, we may have a number of the large nozzles open. If we're testing a little bathroom fan, we may have a very small nozzle open. That's how we can test very large fans, very small fans, all out of the same exact chamber. Okay. And then you have setup methods. Again, I only want to introduce this not to overcomplicate it, but I want to prove a little point whenever I show you a few power roof ventilator examples. So, as you know, we have ducted fans and we have non-ducted fans. Okay. We basically test everything free inlet. I'll explain that here in a few minutes. And then in some cases, we'll have a free inlet, ducted inlet, free outlet, just depending on the fan type. And all these are specified in each one of the catalogs. Again, it's an ideal setup. So for instance, when we look at typical blowers, they're tested free inlet with a equal diameter three diameter outlet on the discharge. I always point this out because a lot of times we'll get calls and engineers will ask if they can put let's say a stack on an upblast blower. And I say yes, as long as they maintain the exact same geometry. A 3 foot stack will actually make the fan work a little bit better. Okay. All right. So, obviously, a prop fan is a free inlet, free outlet test. However, I want to point out that if I put ductwork on the inlet of that fan, let's say 3 diameters of ductwork straight into that fan, that prop fan would actually work a little bit better. Well, obviously, we don't test it that way because that's not a typical installation. Okay. Here's where we're going to get a little bit deeper into understanding the effects of ducted and non-ducted test conditions. Uh, a power roof ventilator. And again, I realize we've got a lot of engineers on here that work on very, very, very complex systems. The reason why I use a power roof ventilator is because typically these are the fans that always show up in air balance reports, okay? Can get kind of frustrating. Well, so if I tell you that I test this fan as a free inlet, free outlet test, okay, I want to point something out very important here. You're probably thinking, wait a minute, what do you normally put on duct? You usually put an inlet duct on a typical power roof ventilator. Well, is that fan going to work better or worse if you put inlet duct on? Believe it or not, if you put a straight inlet duct on that fan, let's say of an equal 3 diameters, you're actually going to get better performance out of that product. And I want to stress better performance. All right. We've got videos on this. If you actually want to see some of the final test results. Okay. So straight duct, you'll actually get a small performance increase. Okay. Right. However, if you don't have a straight duct, you're going to have very reduced performance. Okay. Very important to understand how important a straight duct is into these type fans. All right. And you can see we've actually got this in a video. Same with blowers. Once we put an inlet duct on, we actually get a performance increase. Okay. Uh, One of the points I want to make right here, and it's kind of a brain teaser question, but I like to use it, especially if we consider what we've been through, at least in the northeastern United States and eastern Canada, this winter. Obviously, we've gotten a lot of snow, correct? Well, I like to ask this it's kind of a corny question, it's kind of a brain teaser, but I'll ask engineers with the list, if we're looking at a very small power roof ventilator, which, if I had the identical CFM and static and the identical size power roof ventilator, and I had one up in, let's say, installed in Montreal and one installed in Phoenix, Arizona, I'll ask people, which one will probably work better? And everybody assumes that, well, it's warm weather, so it's probably Phoenix. And I go, no, it's actually the one in Montreal, because probably very similar to here in Toronto or Ontario, you all specify 24-inch high curbs. The 24-inch high curb gives you the added straight length into the fan. In, let's say, Arizona, they'll use a little bitty 8-inch high curb, and it will actually cause a restriction on the fan. So the mere fact that you may use an 18 to 24-inch high curb actually helps your performance on small little power roof ventilators. Just kind of keep that in mind. Okay. So, now I'm going to jump to accessories. If you see any accessory on a fan, it is, in fact, external pressure drop that has to be taken into account. That's not part of the test. Okay. So it's very important to understand. And again, Let me just say something real quick. I know we're kind of coming up on that our 15-minute mark. Uh, we'll hopefully be done in about 10 minutes, and about 10:55 we'll field any questions. Okay. But think about this. With the little power roof ventilator, what do we put between the curb and the fan itself? We put a damper. Well, go back and look at the chart or the handout I gave you for any component. How is a damper tested? It's tested laminar in, laminar out. So you just can't apply the pressure drop of that damper from a chart. It's probably going to be a lot more or double what that pressure drop would say because you've packed everything in together. Okay, so the test does not include any added accessory. Uh, I freely say if I never had to sell any inlet or discharge damper on any of my fans, I would be pretty happy. Anything that immediately blocks the inlet or the discharge is a restriction. We offer the accessory mainly because other manufacturers do, but it's not necessarily a great idea. Okay, so you can see there's a big pressure drop when you put any kind of damper in. Well, uh, obviously, with the use of more EC motors, you're starting to see more low leak motor operated dampers, and you really get a huge performance restriction based on the actuators and everything inside. So, if you want to enhance your design where you can within code, I always recommend taking the damper for that fan if it's motor operated and putting it in a laminar location and put the damper in your damper spec. Okay. Doesn't have to come from us. You can get it in your general damper spec. Okay. We've kind of gone through the whole fan, the understanding of the curves. Okay. So now I want to just talk briefly about the air system and the system curve. Obviously, your actual air system is just made up of a bunch of components, right? Diffusers, duct components. Keep in mind, every one of these items were tested in a lab. And basically, if you want to know how they were tested laminar in, laminar out. Whether it's a duct component with a turning vane, a damper, the fan, the diffuser. I can guarantee you every diffuser or GRD was tested with a laminar drop in that that will affect how well that GRD works. Okay, and again, and that's all followed by a system curve. Okay, all right. So let me kind of speed up here a minute. Uh, System effect. What is system effect? Look, it's when you apply a product into your system that is a little bit different than the way it was tested. Okay. Uh, Keep in mind, all products are tested so you get the full flow potential. If you have restrictions, you're going to get a loss of performance and your data is not going to fall on the fan curve. Okay. That's why we've given you the little guideline for how many diameters in and diameters out. Okay. Again, so why do we say 2.5? Because it allows the airflow to straighten out. Okay. Right. If you look at this, probably this middle example right here is the worst one of all. And let me explain this. Uh, if you look, I've got the identical fan and the identical ductwork component, but this discharge going up or this duct going up, this one going down, you're going to get two totally different performances. Okay. Which is why we're going to talk a little bit about rotations and discharges here in a few minutes. All right. So why do we ask for 3 diameters? Kind of what we call static regain. It allows the air to oh, sorry about that, to straighten out and get back to an even velocity. Okay. And again, and we've given you guidelines on how to handle this. Now, real quick, I'm going to go through this again, kind of real quick, because I know we're coming down on time. I want to get to some of my examples of bad selection. So, for those of you working in Revit, you go, you've got your sheet metal package. I just want to point something out, and basically what it is when you look at a component and the pressure loss out of SMACNA, it's again also based on laminar flow in, laminar flow out. So I like to show this little example. I've got four components. I went to SMACNA. I figured up what the pressure drop would be based on a given velocity. The problem is you add all these up for a total pressure drop. However, this configuration and this configuration, they're not going to match that 0.45 that the SMACNA calculation said you should have. Well, I like to ask this question, is the top more restrictive or the bottom? Well, the bottom is more restrictive because the air turns once. The top, it's usually gonna take a lot more pressure drop because the air is changing and turning twice. Now, what happens with you on jobs is maybe another trade got there before and the contractor has to go around it. Okay, you'll see even little things like this you may not be able to account for in your design, which is, again, the reason why we give you, want you to select in the right spot on the curve and make sure that you're covered. Okay. We even calculated these using CFD. And what we found was, again, the SMACNA SMACNA book said the pressure drop would be 0.45. This one was 0.64. This was actually lower. Well, what would match what the SMACNA guide said? I've got a straight duct in to the elbow, straight into the elbow, straight out of the elbow, straight in. And when we modeled that, that came very close to what SMACNA said. So the point being, when you look at a fitting like that, a simple elbow, SMACNA's data is pretty much based on perfect flow in, perfect flow out. Okay. So you have this with all your components, dampers, coils, filters, airflow stations. Every single component is basically based on that. We also know that you don't have the amount of space all the time. So there are system effect factors, which basically means if you don't have that 2.5 duct diameter condition, you can actually get a guide from AMCA that will tell you how much pressure drop to add whenever you're in that different situation. Okay. Just going to say one thing about air balance reports, and then I'm going to speed up to the pictures. The biggest problem with air balance reports is not necessarily the measurements, but the air balance companies don't show you where they took the readings. I tell people don't even waste time looking at an air balance report unless you know what the inlets look like, what the discharge looks like, and where the system was measured from. Okay, all right. So you have to know what those measurements are in order to get a good velocity profile as opposed to a unsatisfactory velocity profile. Okay. And like I told you, this is where we kind of started. So as long as we know where the components are tested from, you can give me that information. We can always help you out. Okay. So now let's look at some of the interesting field examples. Again, coming down here on time, uh, obviously a bad situation. Hopefully you'll identify this as, again, a bad situation. If you have the understanding that blower right there had a perfect uh, 3 diameter discharge, this was a major, major problem. Okay. Uh, what did I tell you about dampers? I hate them. Okay. If you want to know how we fix this problem or the reduced airflow, we added a straight duct and put put the damper at the end of that duct, and the pressure drop went down. Okay. Here's a job in Indianapolis, Indiana with the Eli Lilly. Uh, Big time architect, big time engineer, big time contractor, and there's a reason they took a picture. Okay. A really bad discharge, really bad inlet, right? And this is where we introduce the importance of understanding the rotations and the discharges. Okay. So you can see they should have had a bottom angular up because we're viewing it from the drive side, and they probably wouldn't have even had any issue at all with the actual flow. Okay. Here's another one in New York. Uh, Not a bad outlet condition, but it could have been a lot better just with a top angular up. All right. This is kind of a funny one again, top angular up. If you're worried about moisture or water getting in the bottom of the fan, all these have drains on them. Easily can be drained out without putting a restricted inlet or discharge on. This was a real disaster job. Real disaster job. It was actually a government lab down in Maryland, and just absolutely was a disaster because nobody knew what rotation and discharge and where to read it from on the to always base it off of the inlet condition or the drive side location. Okay, you can see, and it wasn't just one fan, it was a number of fans where they could have used a bottom angular up, would have been a totally different situation. Okay. And again, you can take a look at these. I've got a number of examples of just disastrous situations. Bottom horizontal here would have worked great, right? Uh, Again, that inlet condition doesn't look that bad, but you can tell where it definitely had a huge effect on the overall fan's performance. Again, we've seen a few like this. We had one similar to this up here in another location just recently that put a huge, huge restriction on the fan. Okay. If you look at this one, again, it was actually a lab damper, not even close to being the performance that the damper said. You didn't have a straight inlet. You've got a flex connector that's sucked in, uh, greatly reducing the flow. This one kind of funny. I kind of feel like this guy was a sculptor, okay, that designed that discharge ductwork, right? Similar situation here on a supply fan. And then we're going to finish up right here. So, if you look at a square fitting with straightening vanes, right? Remember, all these fittings are tested laminar in, laminar out. The angle of the ductwork here made these turning vanes a restriction. Keep that in mind, okay? Just did not work at all. And actually, they had to remove the straightening vanes to make it work. Okay, so there's some great videos at AMCA showing the different system effect conditions. Uh, you can go to AMCA, download them. You can see them on YouTube. We also have a YouTube channel where we have the exact same videos because AMCA did come down to the Cook plant and use our system effect display to produce the educational videos that you have. Okay, so that's it for this. So we'll open it up to any questions that anybody may have. Again, I know that we covered a lot of information there. All right, but if you all want a review, again, come to one of our seminars that we're going to be arranging in the summer and fall, maybe a few in the spring, as well as if you want us to come in and talk about any of this information on during a lunch and learn, we'll be more than happy to do that. Again, just to summarize, no matter how well you've calculated the performance and the CFM requirement on your job, okay, and the pressure drop, if you do not select on the proper part of the fan curve and you don't understand the effects of bad inlets and bad outlets, uh, it can still be a major issue on the job. Okay, so any questions?
Yeah, thank you so much, Ron. We did have a question come in, a few right now. From Ali, why would you prefer bottom angular up over top angular up?
There's no preference. There's no preference. What you want to do is you want to take that sheet that we're going to provide showing all the bottom and top, all the different rotations. We're just showing you that you have a number of different options that you can apply. Okay. That may have been relative to a certain photo. Again, we give the variety just so you can have a good idea of all the options available.
Thanks. Another question that's come in, Ron, from Adam. Does consideration of fan energy index, previously fan efficiency grade, as required by energy standards, affect the process you described for fan selection?
Yes, obviously, the fan efficiency index, okay, is based on if I kind of simplify it, it's kind of a miles per gallon a guide like we have on our cars, right? So if you look at the efficiency index from a fan and a miles per gallon rating on an automobile, okay, uh, those were both tested, and that number was granted based on a certain condition, being a lab condition, or let's say for an automobile on a straight road going a perfectly straight road. Obviously, if you've got more pressure drop or you're going uphill in the automobile, it's going to affect that overall efficiency. Makes sense? So yes, if you have really bad inlets, really bad outlets, a really poor, the wrong rotation and discharge, it's going to affect the efficiency of that equipment.
Thanks, Ron. Jonathan, you had a specific question regarding a cook fan that you have a noise issue with. I'm going to reach out to you after the presentation to discuss those specifics, but Ali has come back again, Ron, regarding the angular discharge, and his question is, for the government lab room, you mentioned they should have used bottom angular up. Why was the bottom angular up advised and not the top angular up?
Got it. Okay. Let me go back to that picture. Okay. Okay. So if you'll notice this right here, Ali, if you can see my screen, can you see my screen right now, or do I need to go back and share?
No, you'll have to share it, Ron.
Oh, okay. Let me go back here and share. Okay. Okay, yeah, okay, now you can see it, right? Okay, Ali, great question. All right. So right up here was a stack. Okay, you can see where my uh, mouse is. This was a stack going straight up to the roof. So if you'll notice, okay, and actually, Ally, I see what you're saying. I actually have that backwards. That uh, should be the other way. Looking at the inlet condition, okay, it should be viewed so we're seeing the airflow go this way and up the stack. So I actually need to correct that, okay? Because that would have been it actually would be much better. So Ali, you get the star of the day on following pointing out a potential issue. That should be the other direction. Gosh, I've got to get that corrected because ultimately what we wanted was the air going, the scroll being bottom angular going this way and then following the way the airflow was supposed to go. So uh, whoever knows Ali, you get a door prize from this presentation. Okay, I need to adjust that. Okay.
Perfect. Thanks, Ron. That's all of the questions that had come in to the chat. So we're a little bit over time, so I think we'll leave it at that for today. But I want to say thank you very much. What an amazing presentation. Appreciate everybody for taking the time this morning and joining us. And thank you very much, Ron, for bringing all this knowledge today for us as well.
Great. And thank you, Ali, for identifying that. I've got to make a little adjustment there. All right.
Great. Thank you, everybody.
Thanks.
Have a great day.
Bye.
Take care.